Hello viewers, this is Dr. Dheeraj Malhotra, and today we are going to start a new data structure tree. Unlike our previously covered data structures, tree is a non-linear data structure and we will explore its detail in today's lecture. So tree is basically a data structure that is used to describe a parent-child relationship between various nodes, or in other words you can say the hierarchical relationship between various nodes. So there are many examples, like in our office we have hierarchy where we have boss, managers, subordinates and so on. So such kind of present things we can easily present via trees. Okay, so conceptually we can represent a tree like this where we have a root node. Okay, and then we have its subordinates, or you can say child nodes, and then further subchild nodes, and like this we can represent a tree conceptually. Okay, so here we have some important definitions related to tree. First of all, node. A node is basically a collection of data with address. Okay, so if you could recall, the node structure of a doubly linked list it's quite similar. Here we also have provision to store two addresses, but unlike linked list, in linked list we usually call it previous or next type of pointers. Here we call it left child or right child, or left pointer or right pointer. Basically it represents that the address of its left child and right child address. Okay, pointers. Fine. So just like this, here in X we need to store the address of Y and Z. Fine. Then we have root. Root is the topmost node of the tree. Okay, so you can say there is no parent to root. Okay, it's the topmost node, and if it is empty, then you can say that the tree is empty. Then parent of a node is immediate predecessor, like for Y it is X. Okay, so if we see here, so for B parent is X, for X parent is A, and so on. It's an immediate predecessor. For Y it is A, for D it is Z, for E it is Z. Okay, these are called parent nodes. Then we have child nodes. Child nodes are the immediate successors. For example, if we consider X, then the child nodes are Y and Z. Okay, and similarly we can have subchild nodes. Okay, if we consider this again, then for A, X, Y, Z are child nodes. For X, B and C are child nodes. For Z, D and E are child nodes. Okay, fine. So then we have leaf nodes. A leaf node is one which doesn't have any child node. Okay, so terminal nodes. So Y and Z are leaf nodes. They are not having any further child. So these are called leaf nodes. Then we also have concept of subtrees. Okay, so for example, here in this complete tree we have two subtrees. One is left subtree and consisting of three nodes B, X and Y, and we have right subtree consisting of two nodes C and Z. This is a concept of subtree. Then we have a concept called path. So path is basically a sequence of edges, okay, which is required to be followed to reach the destination. Okay, so for example, if I ask you to tell the path of X, so by default we always consider the source node as root node. Then we have to describe the path of X from A, so you can say from A to B and then B to X. Similarly, the path of A to Y is given as A to B, B to Y, and so on. Okay, so it is basically a sequence of edges from source node to destination node. Okay, then we have level. Level is basically always assigned from root onwards, and root is always at level 0. Okay, and then we increase level. Okay, so these two nodes are at level 1, then after these three nodes are level 1 plus 1, that is level 2, and so on. Okay, so level is always assigned from root node onwards, and root is always at level 0. Height, you can say it is always level plus 1. Okay, so that means root is at height 1, because root has level 0, then height is level plus 1. Okay, similarly B and C has height of level 1 plus 1, that is 2, and so on. Okay, and the height of an empty tree will be 0, means which doesn't have even a root child. Okay, Then we have descendants. Descendants are successor nodes on a path. Okay, so B, X, Y are descendants of node A. You can say like this: B, X, Y are descendants of node A, and so on. Okay, successor nodes. Fine. Then we have siblings. Siblings are those nodes that possess single parent. For example, X and Y are siblings because they belong to single parent B. Okay, so here sibling of Z is missing. Fine. Then we have degree. Degree means number of children that a node has. For example, degree of B is 2, degree of C is 1. Okay, and so on. Similarly, we have called out degree. Out degree is number of edges leaving a particular node. So, for example, out degree of B is 2, out degree of C is 1, out degree of A is 2. In degree is equal to number of edges arriving at the node. Arriving at the node, for example, for B in degree is 1, for C it is 1, but for root A in degree is 0 because no edges arriving into it. Okay. Then we have concept called depth. Depth is basically the length of path. Path I just told you. It's a sequence of vertices that we need to follow from source to destination, and path is basically the number of nodes which we need to follow. Okay. So for example, length of path from root node to the destination node. For example, if we have considered X, then path may be 2 nodes because from root we need to first traverse A to B and then B to X. Okay. So these are the basic definitions that may be asked in exam, and they usually give you a diagram, and then they will ask you regarding various things like what is the level of Y, what is the height of B, what is the height of complete tree. Similarly, the height of complete tree is maximum level plus 1. Okay, so like this they may ask in your exam. Okay, so you need to memorize all these basic definitions. Fine, now we are starting with a tree concept called binary tree. So as its name indicates, a binary tree has maximum of 2 child. Fine. So when we just call a tree, then the number of child nodes are not fixed. They may be 3, 4 or 5 or maybe 2 or maybe 1. But when we call it binary, then we have maximum 2 childs for each node. Maximum means it can possess 1 child, it can possess also 0 child for a particular node. Okay, so that comes under the definition of binary. So a binary tree can have at most 2 children, that is either a parent can have 0, 1 or at most 2 children. Okay, so this is the meaning of binary tree. So this is basically a type of binary tree. Here A has 2 child and then B has 2 child and so on. Okay, and then we have concept called complete binary tree. A complete binary tree, in order that a binary tree can be categorized as complete, it need to possess at least 2 properties. The first property is that all the levels should be completely filled. Okay, all the levels should be completed filled except the last one may be relaxed. Okay, so for example, let me. Okay, so these are the examples of complete binary tree. Here we can see that A has 2 child, then B has 2 child, and however C doesn't have child, but yes, from left to right childs are filled. For example, in case now this is also an example of complete binary tree. Here we have 1 child of C. So as per definition of binary tree, 1 child is also allowed, but we need to start filling the childs from left to right. For example, if C possesses Z as right child and no left child is present, then it's not a complete binary tree. Or if C has both childs and B doesn't have any child, then it is also not a complete binary tree. Okay, so this is the meaning of complete binary tree, where we have each node having, where each previous level should have should be filled. First of all, previous level should be filled, and nodes should be connected from left to right. Okay, then we have extended binary tree. Extended binary tree is a tree where we have nodes having either 2 child or no child. Means 1 child is not possible. Okay, so these are extended binary trees. They are sometimes also called 2T trees. Okay, so here those childs which are having which are not leaf nodes. These are called internal nodes, and leaf nodes means which doesn't have any child, they are called external nodes. So you can notice I is for internal nodes having further child, E is for external nodes having no further child. Okay, fine. So now we have memory representation of binary trees. How to represent trees in the memory? So there are two possible representations: static representation known as array representation, and dynamic representation known as linked list type of representation, linked representation. Okay, so array representation of binary trees, we need to first keep 3 points in our mind while representing binary tree via array. First of all, the root node is always stored in the first location of array. In C, we usually start indexing from 0, but here we always store root at the first location, means first index of array rather than 0. Secondly, if the parent node is stored at location k, then left child is stored at location 2k and the right child is stored at location 2k plus 1. Okay, so with example, I will just clear you this thing, that if parent is at location k, for example, if root is at first position, then the left child of root is stored at 2 into 1, means second position, and right child is stored at location 2 into 1 plus 1, third location. Okay, then in order to determine the overall size of array required, which is just sufficient to store the tree, is 2 raised to power h minus 1, where h is the height of the tree. So this is the formula to determine the size of the array in order to store the complete tree. Okay, so while filling nodes in the array, we should not come across a situation where we don't have available slot. For example, we calculate the address of each and every left child via this formula and address of each and every right child via this formula. So if, for example, if it is giving us some index and that is not available in the array, then it may be a problematic situation. Okay, so let us first see this thing here. So for example, if we have this tree, so here root is a, so we are going to store it in location 1. In order, now b is the left child of a, so we will apply formula of 2k. If it is at k location, means it is at first location, then 2k means 2 into 1 second location. And g is stored, g is a right child, 2 into 1 plus 1, 2k plus 1. So again see, in order to determine the address of each and every left child, we need to put formula 2k, where k is the address of parent. And in order to determine the address of right child, we need to put this formula 2k plus 1, where k is the address of parent. Okay, so for example, b is at 2 location and c is the left child of b. So how to determine the address of c? b is at 2, so c is the left child, that means 2 into 2, 4. So c is stored at 4th location. Similarly, f is the right child of b, so 2 into 2 plus 1, that means 5th location we will store f. Okay, so similarly you can store any node. For example, h is stored at location 6, then the right child I is to be stored at 2 into 6 plus 1, directly at 13 location. So you may be noticing that few slots are empty because few nodes are missing. For example, we don't have childs of f node, we don't have left child of h, we don't have child of j node. And how to determine the overall this size of array? So here height of tree, height is always level plus 1. So what is the maximum level of this tree? 0, 1, 2, 3. Maximum level is 3. So overall height is 4 because height is level plus 1. So in order to determine the size of array, we need to put this formula 2 raised to power h minus 1. So 2 raised to power 4, that means 16 minus 1, 15. So the size of array we require is 15. Okay. And as far as linked representation, that is similar to the structure of a doubly type. So here we will define the structure like integer type information. If you want to store character type information in tree, then char type, and we need two addresses because in order to define binary tree we need to have two addresses. One is of left child and another one is of right child. So self-referential structure is quite similar to doubly, except that we have renamed prev and next with left child and right child. This is dynamic representation of tree. Okay, so this is how we conceptually actually store inside the memory. So here we have a node and we will store the address of b here and address of c here in the right portion. B doesn't have right child, so we will store here null, and if both childs are missing, then we will store null.